this is only part of the talk, because we are experimentalists in São Carlos, and we are setting up an experiment, as I'll show you. And while things set up, and this is boring, we do some calculations, and this is some part of the calculations we're doing right now. But essentially, I'm showing an overview of what we've been doing there at our lab. This specific topic is a collaboration between our group and Aristeu Lima at Unilab. He will be here, I think, tomorrow, and speaks on Wednesday on some other project. Okay, this is a brief summary of my talk. So I decided to give a brief overview of who and where you are, to give you just scale and a sense of location of atomic physics groups here in Brazil, very briefly. Then I talk about two topics. First, simulations on few beams mod, magneto-optical traps. And the topic that is related to the title of this talk, which is BC in bubble traps. So just like BCs in shells. And actually dipolar BCs in shells. I give you what is done, what has been done recently on non-dipolar BCs, and then what we want to do from an experimentalist point of view, and some of the calculations we are doing there. And so there's not much fancy stuff here, not much quasi-quantum crystals and so on. All the language is very simple, actually. All the simulations, all the calculations are very simple, so take this as theory made by experimentalists. I think this is a good definition of the things we are showing. Good. So who and where we are. So we are in São Carlos, in the countryside of São Paulo state, and there we have two large physics institutes, one at University of São Paulo and one at a federal university. And we are by far the largest center for ultra-cold atoms in Brazil. At the University of São Paulo, the head of the group is Professor Vanderlei Banhato. But we have also Professor Luiz Marcaça working with Rydbergs, Philippe Courtet, Monica, who is speaking just after me, and myself working on ultra-cold atoms. And in the Federal University, we have a strong theory group led by Ednilson Santos and Romain Bachelard, and some starting experiments with Raul and Rodrigo Shiozaki. Good, and everyone is financed by the state funding agency, which is FAPESP, under this big center for optics and photonics. So somehow we identify ourselves as a single group. Okay, this is Brazil. I'm sure you know it. We are here in Natal, and São Carlos is there. And to give a sense of scale, this is about 3,000 kilometers from here. And for you that are coming back to Europe, this is more than half the distance to Lisbon. And Brazil goes straight down. Although we are the largest center for ultra-cold atoms here, we have also people working with this in Recife, which is close by. Márcio is speaking tomorrow, I think. And a large group at São Paulo City. Rafael is also speaking at this conference on Wednesday, I think. And then there's Tommaso here, there is Aristeu close by, and so on. Good. Okay, about our group, as I said, we are building up an experiment to study dysprosium atoms. And right now we are in the boring phase that we have to do vacuum, we have to do lasers, we have to do optics, everything really from scratch. So I'm not going into these details because this is essentially old things. So all experimentalists went through this at some point. There's nothing new here. But then the first question is why dysprosium? And if you were here last week and heard Tillman speaking, you know that these dipolar gases have grown in the last few years with great physics being done. These low field flashbar resonances, the droplets that we have heard recently, and all these phenomena that have been investigated by Tillman, Franciscan in Innsbruck, then there is Florence, Paris, and so on. And the reason behind dysprosium is this is the most magnetic atom in the periodic table. This has a total 10 Bohr magneton in the ground state. So if you want to do dipolar physics with atoms, one has to choose this kind of thing. And of course, one can have a complex electronic and collisional properties because you have a D open, F open shell under an S shell, so there can be collisional interesting properties. There are bosonic and fermionic isotopes, as I said, low field flashbar resonances. One can even study variation of fundamental constants, and of course, since a few years, we know that it's possible to laser cool and trap these samples. Good, but then since we're doing all these instrumental parts of the experiment, we had to do something else, and then we started doing some calculations. First one is on this topic, few beams magneto-optical traps. I think any experimentalist would agree that we don't pay any more much attention to magneto-optical trapping, but this is one of the main tools that we have to pre-cool, collect atoms to achieve our Bose-Einstein condensate, Fermi gases, and so on. And it's essential to the experiment. We don't pay any more attention, but this is needed. And well, the simple model is known. No, you have a magnetic field that open the degeneracy of the levels of an excited state, and combined with polarizations of the light beams, you create a force that is position dependent. So it pushes the atoms towards the center, keeping them around the center of the trap. Simple like this. Good. The scattering force is given by that. So just the momentum given by a photon and the probability that it's scattered. And usually, one doesn't care about gravity. The maximum force given by this is much, much larger than gravity, like several orders of magnitude. But if the transitions are narrow, like on the order of kilohertz or hundreds of kilohertz, this is not anymore true, and gravity plays a role in the trap. This has been seen quite some time ago in a erbium mod, a regular 6-beam erbium mod, seen gravitational sag. So this is experimental sequencing, but what I want to show you is that atoms, they are not falling under gravity. There is the trap here. They are just sagging because of gravity force. So the equilibrium point is below the geometrical center of the trap. So we know that gravity is playing some role at this kind of setup. Then, very recently, Francesca Ferlaino in Innsbruck has shown in a very beautiful experiment a double mod of erbium and dysprosium with only 5 beams, removing the beam that comes from the top and using gravity to balance things. So this is a 5-beam mod, and they see they can see atoms trapped in the 6-beam mode, in the 5-beam mode for erbium, for dysprosium. And, well, great. For them, it's great, because then they can have, I think, a microscope objective from here. And then when we saw this, we asked ourselves, okay, can we go further? So let's play around with scattering forces, because this we can do. And let's try. Let's give it a try. So can we do less than 5-beam mode? And then what we started doing was, what are the advantages of this? First, you have a better optical access. This is always a problem for experimentalists. And, well, we have in principle, a simple optical configuration. But to be fair, our main motivation behind this is just to show a very funny application of light-matter interaction. So if we can demonstrate this, it's another point in favor of this very powerful tool that we have for quite some time in our hands. Good, so we investigate the possibility then of creating a 4-beam and a 3-beam magneto-optical trap, specifically for dysprosium, because this is our interest, but it would work in narrow line cooling transition. So it should work for strontium, for erbium, for just pick the line. Good, so the 4-beam mode would be like this. This is very similar to what Jean Dalibard has in Paris. So 2 beams like this, 2 beams, one entering the plane of the screen, one outside. Coils are here, also in the plane of the screen. Gravity is pointing down. We make simulations on this configuration. And we also make simulations on this configuration. So this is a 3D view. This is like a pyramid. And I must say, in São Carlos, we have an atomic fountain for cesium that works exactly like this with 2 pyramids. So no beam on the z-axis, so 2 pyramids. So that's where it comes from. Can we take out the upper beams and just look at this? And we are looking at this configuration to see if it traps atoms. So, and if you look from the top in the plane, they look like this. And what we get, so these are the methods. Essentially, we do full simulation, taking into account local magnetic fields, local polarizations, transition probabilities, probabilities of emitting photons, and so on. We get the velocity and position histogram from the atoms. And we can calculate then trap depth. We can calculate how long they stay, which are the final velocities calculations. And the nice thing about it is that doing that, I should go back one slide. Yeah, sorry. Doing this, we can reproduce Francesca's results very well. So the range of the tunings, where the atom number distribution peaks. So also for the 6-beam, for the 5-beam, also for dysprosium, the 6-beam, the 5, we reproduce everything. So we are confident that this should work for 4 and 3, at least for the simulations. And what we get outside of our simulations is, yes, we can have designed these traps, like I've shown you the pictures, but I'm not showing the results, because we have then at a poster tomorrow afternoon, so the details on the trap depth, how are these the details on the calculations and so on. We have the poster by my postdoc, Ramon, which is here in the audience, showing everything. So now we are working towards the experimental demonstration of this. Since it works very well in simulation, we want to test for real. Good. So then we started looking at this problem. BCs in bubble-like traps. So recently it appeared this publication. So in Physical Review A, Static and Dynamic Properties of Shell-Shaped Condensates in the group of Leonard. And this is not the first publication in shell-like, bubble-like traps, but it's one that essentially goes through the whole basic properties that one would think of. So they just calculate the density distributions from the fillet sphere towards the very thin shell trap, so for the whole spectrum. And they also calculate the collective excitations for the whole thing, again from the fillet to the very thin shell. And the motivation behind this theoretical investigation are three essentially. First, this is an interesting problem to look for a dimensional crossover that one can look at it continuously from fillet to the hollow sphere, because you essentially tune the geometry with changing RF fields. This is a magnetic trap dressed with RF fields. So you can look continuously at this. And this is, when the inner boundary appears, this is a change in the topology of the system, and a direct change, because you're really changing, you're creating a new boundary on the system. And the third motivation is that, it's in the next slides, but I'll show in a second. So they have equilibrium densities. You see, for the fillet sphere, this delta is just a parameter that gives RF intensity. So it's giving how this thing is hollowing. And they calculate the densities and the oscillation frequencies, the collective mode frequencies. And indeed, this is how they want to see the transition, because if you're an experimentalist, you know you look in a 2D projection of your trap, so you never see if it's hollow or not. But this you can measure with a very high accuracy, so one can really see if the thing is hollowing, looking at collective modes. And this is how they propose to do it. But to do it in Earth is very difficult because of gravity. So, and this is what they see, and this has been seen in real experiments actually. So for 0G, for 0.0014 G, you have already nothing at the top. So this is a problem, and this is the third motivation. There is a cold atom laboratory in space now, at the space station. And this is one of the experiments that they were sending to space. So I think we'll hear from this soon in the experimental side. Good. This appeared, we were thinking about shell-like things, so we started looking at the problem with dipoles. So why not having a collection of dipoles in the surface of a sphere? Let's look at it again from an experimentalist point of view, so in the most simple configurations possible. So we have externally polarized dipoles. We have a thin shell, so this is something that I like, because this geometrically is a two-dimensional problem, but interaction is still 3D. So atoms see each other across the bubble. And contrary to 2D problems, usual 2D problems, dipoles are not perpendicular to the surface, but change their orientation as you move in the sphere. So this is essentially this problem. No, you have a sphere and dipoles on the surface only, Okay. Now, what's our feeling? We sat down to discuss this, and this is our experimentalist point of view. Up there, we should have dipole-dipole interaction that is repulsive, or the dominant term should be the repulsive one. Then, if you move along a theta line, so if you move like this, you should have dominant attractive dipole-dipole interaction, but attractive repulsive along a circle like this, along phi. And then we expect here to have azimuthal symmetry, so this we could now rotate the sphere and see, we should see no changes. We are of course working on the Finchal limit, so geometrically should be a 2D problem, and we expect at least a pi periodicity, or in other words, what happens at the North Pole should be the same at the South Pole. We don't expect changes. How this behaves on going from north to south, this is what we want to calculate, but we expect that it reproduces what is there here. Actually, this, as I show you, we impose on our calculations. This we let free and see what happens. So, formal approach, we write Gross-Pitaevsky equation. This is the bubble trap potential, so a trap frequency and harmonic potential away from the center of the system. So we write an ansatz, so we just write a Gaussian for the radial part, so this is just the Finchal limit. And we write the radial part like this, so a sum of harmonic spherics. And then, since we impose azimuthal symmetry, M is always 0. Okay, this is our problem. And then we started making calculations with this, and we have to minimize energy. And when I was preparing the talk, I was going to, okay, let's add the expressions. And they were not fitting the slide, so it's too big. So you have to trust me that we calculated those things. And what we see when we minimize energy is that odd L's show vanishing amplitude, even L's show this is wrong, show appreciable amplitude. So North Pole and South Pole are essentially the same. And then we have to see ground state density distributions. And so we cannot sum L for forever, so we do a sum, we calculate the energy summing until 0, until 2, until 4, and so on. And what we see is that we have a minimum at 2, so this is also what we see, that 2 is probably the dominant mode, so we sum up to this. And what we see is not what we expected, and I want to stress this is preliminary results in my second but last slide. So for very high contact interactions, we see essentially a flat distribution like a non-dipolar BC. But when I decrease contact interactions, we are expecting atoms to this is a theta line, so 0 is North Pole, pi is South Pole. We were expecting atoms to bunch here at equator, like we are all now. And we see the contrary, we see they going to the poles. So it's not clear to us why is that. This is countering our intuition. and we are trying to really understand this. So, of course, I have someone working very hard on rechecking calculations to be sure, but actually this is what we see. So for the experimental feasibility, so shell traps, as I said, are formed in magnetic trap dressed with RF. So this is a problem for dipolar atoms, for real experiments, because magnetic traps mean dipolar relaxation, so it's not clear how this is going to be for dipoles. We cannot do magnetic levitation because of this. And of course, we need a microgravity experiment. So either in the space station or the drop tower, like the one in Hanover or so. Of course, we are trying to make sense of these counterintuitive results. We are double-checking calculations, and we are, from that, evaluating collective modes on the thin shell. Of course, this problem is very rich if one opens the thin shell restriction, and we see how this goes forward. Okay, so these are just what I've shown you, and this is my team. So Pedro and Eduardo are taking care of this shell experiment. Ramon, who is here, is taking care of this mod experiment. We have funding from FAPESP, CAPES, and the Humboldt Foundation. So thank you for your attention, and check the poster tomorrow.
Thank you, Emanuel.
So if I have seen correctly, when one goes from 6 to 5 beams, you lose about